Good evening, guys. We're going to try to do some night sky imaging of deep space. I had a little time before going on this stream to do some work with the two telescopes I'm going to be using that are now ready to get into action. I'll show you those two scopes. Let me bring up it's gone offline. Let's, okay. I think we're good now. This telescope is a wide field telescope, and I was imaging part of the Flame Nebula, and I ran into some mechanical problems. I was just too cold to go outside and try to figure out what was going on, so I parked the scope. This telescope right now is imaging a very faint nebula, and we'll take a look at that. I'm not too sure I'm going to continue with that target. In fact, I'm pretty sure I'm going to make a change. It is so faint that I really need a different kit to work on that. But I wanted to give it a try while I was waiting to go online. This telescope is a 625 millimeter telescope. Normally, if you've seen my prior streaming efforts, I usually have an 8-inch Smith Cassegrain, which has much more focal length, and I took that off to do some work on it and put the Vixen on, this 625. This is 330 millimeter, a even wider field telescope. So I'm also using something different on this telescope. I'm using what I call a one-shot color camera. There is no, I do have a filter for ultraviolet and an IR cut filter that will help to minimize the light pollution, especially if and when the moon gets in the picture and starts lighting up the night sky. It's a waning crescent moon, so we're not going to have a lot of influence from it, and it's going to rise later tonight. So right now we don't have any issues with it at all. But at any rate, I'm not sure if I'm going to have mechanical problems with this mount or not. And if I am, I'm probably just going to run this one, and I'll go out and fix it tomorrow when it's a little warmer, when the sun's out, and I can see better. So with that being said, let's go back to EMOI. And I'm going to share my screen and show you the issues that well, maybe we won't have them. Let's go there now. And I'm hoping, let's see, we're on scope number 1, and that's the problem scope. I was imaging the Flame Nebula, and that's when the mount began to act up. In fact, I'll show you what happened. I marked this picture as bad, but when it started to act up, the telescope moves sufficient enough to cause these blurs, so it's an unusable image. I'll go back to the image prior to that, and you can see that stars are fine here. I'll do a medium stretch. This is what's called the Flame Nebula. This is another part of the flame. It's a lot of nebulosity in the right-hand corner, but this is the flame going up. It's kind of faint. In fact, I'm not sure if it's going to be easy for you to see, but let me also do something real quick here. I want to double check. and making some adjustments. I don't think that's going to make any difference, but let's see. We're going to uncheck the Flame Nebula, and I made a decision that I'm going to uncheck these three galaxies that are clustered together. Let me tell you something else that could have happened. The wind is wicked outside. I haven't ever seen the wind create that big of a problem with an image. I've seen it cause a problem, but not that big of a problem. So at any rate, let's go to the Whirlpool Galaxy. I want to double check and make sure it's at a good part in the sky. I'm going to click on Planning Tools, and actually it's kind of low. It's at 39 degrees, but I'm going to go ahead. No, actually it's at 30 degrees. And no, it's not. That's when we were going to start it. Let me just get rid of this. It's at 40 degrees, 39, 40 degrees. We're good. Okay. Let's go ahead and let's bring up my. Let's do this again. Let's bring up. This is the other camera that's working. The one shot. Let's make sure that. I don't think I'm going to stay with, let's stretch this a little bit more. It is a faint nebulosity. A lot of star clusters here. You notice these little checkerboard patterns. That's pretty characteristic of a one-shot color camera, as in a DSLR. This happens to be, though, an astroimaging camera, but they use what's called a Bayer matrix. And this matrix is like a checkerboard, and in each one of these little squares there are receptors, and one of those receptors acknowledges the color red, one absorbs the color blue, and two of the receptors take on green. So there's two green receptors, one blue and one red. And the reason for that is that there is a predominance of green, the color green, in the universe, and camera manufacturers know that. And so that's why all Bayer matrix sensors have the two green, one blue, and one red receptor for each photocell. As the photons leave the image and travel through time and strike the sensor, the green will be acknowledged by the green receptors, and the blue and the red will also acknowledge. The problem with a one-shot color camera is that if you're imaging a target that's rich in, say, oxygen, then it's going to be emitting a lot of the color blue. And only 1/4 of your photocells, or 1/4 of your sensor, will absorb the color blue. 1/4 will absorb the color red, and 1/2 the color green. So unless you have a part of the sky that you're imaging that has some greenish tones to it, then your sensor will be less effective. And for that reason, when you use a one-shot color camera, you have to take more images and stack them in order to gain enough photon data that you got an image. But when you see this checkerboard, that's all it is. And when you de-Bayer the image, the checkerboard disappears. And that's when you convert the image actually into a color rendering. So we have taken 6 frames. I'm looking at the bottom here, and these are 6 500 or 300-second 5-minute frames. And as I mentioned, I'm using an IR UV cut filter. So I think what I'm going to do is I'm going to go ahead and pause this one, And as soon as this finishes in 200 seconds, I'm going to move this one also to the Whirlpool Galaxy. I think I'm going to use both telescopes to image the Whirlpool Galaxy. Let's look at that for a minute. And that's M51. And let's just type in M51. And it'll take us to it. And here we are. And again, it's get the right time here. The Whirlpool Galaxy is going to move throughout the night sky this way, and then it'll cross the northern meridian. Let's find out what time it's going to do that. Transit at 2:19. So at 2 o'clock in the morning, it's going to cross the meridian, and then it will be hitting about the 30th latitude limit, and that's probably going to be somewhere around 5:30 or 6 o'clock, which will be too late to be imaging. So I'll image as it goes through the meridian. It'll do a meridian flip, and then it'll end up somewhere over here, probably around 4 o'clock, when I'll schedule the imaging to stop. My plan is to be sound asleep and let these telescopes just take over for me. Let's move back to our outside, and we are still logged on. So let me see. This is telescope number 1, Astro 1, which is the very first one that's currently parked. And we're on the Whirlpool. Let's go ahead and slew to it. And what I'm going to do, I'm going to stop this. What I'm going to do, I'll show you what I do. I have unchecked these other 2 targets. And I'm going to click on this little wheel, which brings up my target settings. And I'm going to click on slew to, and it's asking me if I want to slew to these coordinates. And so I have 13 hours, 30 minutes, and 17 seconds over 47, 16, 33. This is right ascension and deck. And those two intersect at a point in the sky where you'll always find M51. So I'm going to go ahead and say, let's go there. And let's move now to the outside cameras. And we're watching as this Stellarvue 70 ST slews to about 40 degrees in the sky, and that's looks like it's pretty close. I'm going to go ahead and tell it now to center it, and what it's going to do, it's going to take a picture. I'll bring this back up. It's going to take a picture right now, and then we don't need it, as a reference of the sky. And then it's going to do a process called plate solving. It comes from when in years ago, where they would hold up photographic plates and try to locate places in the sky. And what this does, it takes a picture, and then it compares that picture with a catalog of the sky, and it will then center the telescope at that intersection of those coordinates, and it's done that. It is there's an error. It's 55 pixels off in RA, and it's 18 pixels off in DEC. I could run it again and get closer, but that's fine. So we are now in a position to start taking some pictures. I'm going to take L for luminosity. It's a filter that it's kind of like a light pollution filter that I have attached. I'm going to take a 60-second. Let's see. I got the Stellarvue. Let's take a 40-second and let's take about 50 of those. Then I'm also going to take some red. I need to add the red suffix, and we're going to take about 90 seconds of red. Let's make it 90 seconds of red, and let's take 50 of those. Let's add the green filter, and we'll take 90 of those, and finally the blue filter, and we'll look at for the blue suffix, and we'll take at 90 seconds, we'll take 50 of those. 50. Let's go ahead and sleep. We don't need you right now. I have the outside camera set up so that I can, it doesn't stay on all the time. It's powered by, it's got a solar panel that powers the camera, but if it stayed on all the time, it would probably die. So I have it shutting off after I've finished with it, and it automatically does that. That's I keep fighting at night. But I want to be able to use it when I need it, and I don't want to draw down the battery power and then need it and have to run outside to see what's going on. Okay, we're ready to go. It says that the combination of all of these LRGB 40 and 90 second images, taking 50 of them is going to add up to 3 hours. Let's do a little math. I'm going to bring this back up, and I'm going to click on Planning Tools. And this is another way of looking at that planetarium program that we were looking at a while ago. Here's where currently at 40 degrees this galaxy is located, and it's going to transit at 216, which is the zenith of this curve, and then it's going to fall in the west, and it's going to be about this is by the way, the sun has come up over here, and that's what you're seeing. So I'm going to probably stop it right there, and that'll be 5:30. So I can image from 10 to 5:30, and so that's 7.5 hours that I can get in tonight. So knowing that, let's go ahead and we've got 4 hours and 18 minutes now. So let's add, let's go up 70, 70, 70, 70. And we now have 6 hours of imaging time. I don't want to use the entire 7.5 because there's going to be focusing changes going on. For every 2 degree temperature change, I have this program to refocus the telescope automatically. Also, it'll refocus after every filter change, because each filter is not exactly this identical to each other. But at any rate, so we have them refocusing throughout the night, and that takes some time. Also, I dither between pictures, and dithering is a way to manage the noise that appears in long exposure images. In what you're actually doing when you dither is that you're telling the mount to move a few pixels after every picture, and what that does is it creates some randomness, whereas the noise appears at the same place but the stars move. So I can minus out that does not move, which is the hot pixels and the noise. It's not as complicated as it sounds, but it's dithering is a practice that is almost always used by anybody taking deep space, long exposure images. All right, we've got to start our guiding, and we have it going on now. And this is where we're going to find out if we got mount problems. Let's give it a minute and see how the graph looks. This happened to be the telescope that went nuts on me. And it could be wind, but I just don't think that would have created that big of an issue. I look at this RMS number, and this helps me to understand how my guiding's going. This is fine. If I'm around 1 arc second, then I'm happy, and I really didn't pay a whole lot of attention to what our seeing conditions are outside, but anything less than 1 arc second for me in my equipment, I consider to be really good, or good enough to get images without any issues. I don't know what happened a while ago. I wasn't paying a lot of attention to it, but something happened and caused the mount to go nuts, and I just stopped it. And now we're going to go ahead and start imaging this galaxy. One thing I want to point out, I guessed quickly at these exposure times. I'm going to change something here quickly. I've got the default gain at 139. I'm going to change that to 0, and I'm going to have the offset set to 10. And this is a pretty bright galaxy, and I think that will work, but we're going to find out. Let's go ahead and click on resume and see if okay, we got a rotator problem, so we want to just disable it. Let's try it again, and now we're off and running. Down at the bottom, oh mercy, let me pause it. It's waiting until 9:54 to start, because a while ago I clicked start at 9:54 and end. I'm gonna leave end at 5:26 because I'll be in bed and I want it to go ahead and shut down by itself at that time. So we paused. Now let's go ahead and reset this. And sequence, reset sequence, preserve, okay, and let's go. Well, we're trying to. All right, try this. No, we did do that. All right. We reset it. And okay, we're rocking and rolling. I don't it started on its own. I don't know what I did to start it, but we're down to 6 seconds on the first frame. It lost me. Here we go. Okay, we now have our first picture, wide field picture. Let's zoom up about 50%. And this is the Whirlpool Galaxy. It has a companion galaxy that the two are extremely close by, and there's a lot of science behind those two galaxies. I'm going to run over to my planetarium software, and I'll show you a description. Here is what it will look like when I'm finished processing it. But this is the companion galaxy, and it's kind of a pretty. It's a neat galaxy to image. I've imaged it quite a few times over time. And we don't need that. We need to go back to. We don't need to do that either. We need to go back to this, and then let's click on our other. We pause this, and let's go to the Whirlpool Galaxy also with this telescope. Now this telescope will give us a bigger, will fill the frame pretty much with the Whirlpool because it's got twice the focal length. Let me turn on my outside cameras, and this Vixen telescope is the one we're going to take to the Whirlpool Galaxy, and essentially it's going to be in the same alignment that the Stellar View is. So let's go to oh mercy, it's taking another picture. Let me stop that. Abort. Okay, now let's go back to this. Let's click on sequence, preserve progress, and let's make sure we didn't turn off our outside cameras. Nope, we're still good. All right, let's try slewing, and it should be getting. Here we go. That noise you hear, I forgot to stop the guiding program, so we're going to do that now. And let's go back and check our. Okay, we have slewed. Let's center it now. And take a minute. These are actually 15-second plate solve exposures. It's kind of long. I don't need to. I don't need that long. And it's found a plate, and it's going to recenter, hopefully with the galaxy smack dab in the center. We're 918 pixels off in right ascension, and we're 31 off in dec. There's the galaxy, and we really need it smack dab in the center. So it's going to nudge them out, take another picture, make the adjustments. There we go. And it's probably still not in the center, but I can work with that. Oh, we are dead center. We'd have 0 error in RA and 0 error in dec. So it doesn't get any better than that. Let's start our guiding back. We need to start looping. We're taking new pictures, and then we can start guiding. Let's clear out the old graph. Clear that. Clear that. And so we're going to begin guiding. Let's make sure we're now this isn't good. We're starting off with a RMS error of 169, and again we need to be somewhere in the 1 range. I want to clear it. Start again. It does need some settling time. Okay, that's better. It's gonna level out. Um, we really don't need that now. We can put it to sleep, and it won't bother me again until I need it. Let's bring up our window so we can start exposing. And let's see, what have I decided to do here? I'm going to the filter I'm going to use is this IRUV. I think I'm going to take a 180 second exposure. This is an f7 telescope, where the other telescope is f4.7, so it's a lot faster. And this much might be too much in the way of exposure, but let's try, let's go ahead and add about 100 frames. Again, remember, we got about 5 hours of, or 6 hours of imaging time. Actually, we can use almost close to 7, because I won't be going through filter changes, and I won't be refocusing due to filter changes. And so we might be able to get 150 images. And at 7:30, let's try 130 images, and let's just leave it at that. So if I get 130 3-minute images and stack those together, I ought to have some pretty decent detail. Let's go ahead and see. Let's start running it, and let's see what we get. Our guiding's going good. It's going to do a focus. And again, before I start any imaging session, I have it set up to automatically run an autofocus routine. Outside on the telescopes, there is a electronic focuser, and what it does is it takes a series of pictures. The first thing it does is it moves it out of focus outwardly, and it takes a picture. Then it starts bringing it back in, takes another picture, brings it back in, takes another picture, brings it back in, and then when it starts to get smaller again, it goes back out and back out and back out. And what it will do is it will create a curve, kind of a V curve, and where those lines intersect will be the best focus that we'll be able to get during this particular time. As the temperature drops, the elements in the telescope cool, and as you know, temperature expands and contracts everything's affected by it. So the camera's optical train will expand and contract with the temperature, and that affects focus. So each time the temperature drops by 2 degrees, this thing is designed to automatically focus. Let me bring this up. This is a power box that's attached to each of the telescopes outside. Each one has their own independent power box. But if I click over here to the environmental graph, you can see that I have the dew point and the relative humidity being tracked. And since I've started, the temperature and the relative humidity is being, or dew point is being tracked, and that's a function of relative humidity. So this is, the red line is the temperature, and it's dropping, and then the dew point has not changed, which is still a bit unusual. It's usually going up because humidity goes up at night. So let's look and see. We're at 39 degrees right now, and the dew point is at 16. When the dew point and the temperature get close, that's when you start forming moisture on your, that's when you start getting moisture on everything outside. So I know they're calling for a frost tonight, but so far I don't see it yet. At any rate, I have what are called dew heaters, which are straps that are wrapped around the telescope, and those straps heat up, and it keeps dew from forming. Let's go out here and I'll show you what I'm talking about. It keeps dew from forming on the telescopes. This strap right here and this strap right here, and then there's a strap on the guide scope, on each of the guide scope, and they're attached to this power box. And this power box will turn these dew heaters on down here, but there's no need to do it, so they're turned off. So as soon as these two things start getting close, then it will fire up the dew heaters, and that's what you'll see. You'll see lines graphing across here as to how much power is being used to or is being drawn. That's important for people that don't have AC outside. Now I have AC outside, but a lot of these kits are set up and ran by battery power. Particularly when they go off to a dark site, go to a star party, and so you're going to manage your power as best you can, so that if you're going to be there 2 or 3 nights, that you've got enough power to do the imaging you came to do, or you're out of luck. Okay, we're back to we have taken a number of images, or have we? No, we haven't gotten our first image yet. We're taking 182nd frames. We're at 76. So let me get out of here and see this was the plate solving picture that was taken. And while that's counting down 50 seconds, I'm going to go over and look at the other telescope. And here's our very wide field picture of our galaxy. This is the main and the companion galaxy. I think this galaxy here is just eating this one and pulling all of its hydrogen away. And that's what I believe is going on here. But this is going to be also simultaneously put on my YouTube channel. And when I screw up, I'm often reminded, I'm always reminded that no, that's not what's happening. And I tell you, that's how I learn. People that do know what's happening will straighten me out. Seems like that's how I've learned almost everything going through life, screwing up and then having somebody fix it and straighten me out. All right, let's go back and see if the other image is going to be any bigger. It is. The matrix is causing an issue. Let's, as far as visually seeing this, let me also unstretch this a little bit and bring this back some. And then we're going to, let's see if we can't fit this to the screen in a way that we get rid of the bear pattern. I'm trying to do that. All right, I think we did. Matter of fact, let's go up 50%. Okay. And I'm going to move this a little bit over towards the center. Okay, there we go. This is M51, Messier 51, the Whirlpool Galaxy. And it's hard to imagine the detail that you'll be able to see when you have one image and you're looking at one image. But when you have 130 images and you stack them one on top of the other, and you get rid of the noise, the hot pixels, and all you retain and keep is the signal, then that's when the detail becomes really manageable, and you can enhance the colors if you need to, which I usually do, and make modifications where they need to be made, cropping, framing, and those things. So it looks like we're off and running. Let's check the guiding. This was on the second camera. Remember I mentioned dithering, where we move the mount? Well, here's a dither, and it took place, and you can see that the arc values changed on this graph because I automatically commanded the mount to move a few pixels. And when you go through the pictures very quickly, you'll see that everything's moving. They're not stacked on top of each other, and that's by design. So that's working fine. Let's go back to our main screen on this is Astro Imaging Camera number 2. And if we go outside, that's this one right here. This is number 1. And we've got, our second picture. And again, this is a 180-second picture, image, 180-second image. 3 minutes. The sensor was open, and I'm going to lock this range so it doesn't change on me again. Let's see how far away this galaxy is. M51, they'll tell us here, is one of the most conspicuous and best known spiral galaxies in the sky. It is interacting with its much smaller neighbor, NGC 5195. The two galaxies may be seen with binoculars. Well, Charles Messier discovered M51 in 1773. It's going down the Whirlpool spiral pattern, was not seen until 1845. Showpiece in the sky. Bulk and properties. The supernova have been discovered in M51. 19941 is the first. Then SN 2005 is another. There was one in 2005. It's 23 million light years away. Okay. Here's the deal, folks. 23 million light years away. Light can travel around our Earth at the equator 7.5 times in 1 second. That's how fast light travels. It makes that distance 7.5 times in 1 second. Then imagine light traveling for a year. How can you imagine light traveling for a year if it can go around our Earth 7.5 times in 1 second? So how many seconds in a year? Multiply that times 7.5, and that's, you get crazy numbers. But 23 million years. So here is the marvelous thing about deep space imaging to me. The light that's showing up right here has been traveling for 23 million years to get here. And this is not, there's targets that are billion light years away to image. But think about that. 23 million light years away. So for 23 million years, this light's been traveling. And now it just hit my sensor, and you're seeing it. What was going on in the world 23 million years ago? I find that fascinating. I go on Google, and I'll just Google what was happening on Earth 23 million years ago, and it brings up a pretty interesting graphic that does show all the way back to the beginning of Earth what was going on at different periods. But think about that. It's a long time. Alrighty. Let's go back to the other telescope and make sure that one hasn't gone crazy, because that was the one that was acting up on me. So far, it seems to be pretty good, although I see some crazy things happening in over here. Well, we had a dither, and this thing is... We're not getting the best RMS values. We're at 148, and I like it to be at 1 or under. So that's not necessarily good. In fact, it's kind of bad. I imagine we're going to see the stars aren't as sharp. They aren't as tight. But the other telescope, both of these telescopes right now are aimed and photographing the exact same target. One is this one has a wider focal point, and it has a mono camera, and down here you see the filter wheel, and it will change filters. This one has a color camera. I call it a one-shot color camera, and it has a wider focal length. This is 330. This is 625. And both of these have guide scopes on them. And these guide scopes are taking pictures of the same part of the sky. And if the mount seems to want to go in one direction it shouldn't be going, then this guide scope will send a correction. Its only purpose is to send corrections to the mount to keep it pixel on pixel. And it does it through this program called PhD Guiding, PhD2. And the whole purpose of PhD is to make these corrections, which it's doing. You can't really see it, but there's a red line up here that shows that it made a pretty emphatic correction to bring it back closer to center. It kept making them to bring it back closer to center. When you see a blue, here's one that the RA began to go a little crazy, and so it sent a pulse to bring it back. And right up here you have my RA has a 75.75 RMS. My deck is what's off, and I have to deal with a lot of backlash on this mount from time to time. I'm not sure if that's the problem or if it's just not. I know I'm well polar aligned, and you have to polar align these scopes. Now that's showing a much more stable RA and deck behavior, but at any rate, overall it's not doing that great. But the stars are manageable. I can work with that. When I get in post-processing, I can manage these stars, get a little more sharpness out of them. I have to do a lot of fixing up sometimes with data that gets affected by high winds or poor mechanical behavior per that night. I tell you what, anything in the world can mess this up. From time to time, a car will go by that has that heavy bass radio in it, and you can almost feel it come in the house. If you happen to be guiding and watching your guide graphs, you'll see your guide graph move. That boom, boom kind of effect will cause fluctuations in your guide graph. So they're that sensitive, but when you consider that they're fixed on a spot way out 23 million light years away, excuse me, that any movement at all, a cable snag or a cable dragging in the wind, that can do it. Okay, well, I'm going to continue imaging all night long, but I wanted to give you a shot at what I was going to start doing, and we're going to image M51 all night long. As soon as I process this target, I will put it up on Facebook. I will do both the wide field and the more narrow focal length, and that's a promise. I will tomorrow I'm going to be making some changes, and I'm going to, let's go down here, I'm going to take these 4 telescopes. I'm going to be imaging the sun. Well, I take that back. We've got soccer games. My grands have soccer games tomorrow, so I don't know if I'll be imaging the sun tomorrow. But this telescope has solar equipment on it for imaging the sun. This telescope is going to be imaging tomorrow night, and then I'm going to swap the Vixen out for the Smith Cassegrain. This is a Newtonian, and this is a Smith Cassegrain. The wide field Stellaview will stay. That's the one currently imaging with the mono camera. So all of these will have mono cameras. In fact, all 4 scopes. I use a mono camera on the sun when I image it too. Okay, guys. Well, I think we are pretty much done for the night. Thanks for sticking around if you did, and I hope you found something worth watching. Until then, catch you guys later. I'll be on probably tomorrow night about the same time, 9:30, imaging. I'll more than likely go live, and we'll probably pick up a new target. And one of these nights, because we have like 5 or 6 days of clear skies, one of these nights I'm going to, before the moon just disappears, and it'll be later in the night because it's rising later, but we'll go take a look at the moon. It ought to really be nice to image it now, because it's we'll see a lot of shadows. It's getting that crescent look, and so it's the best time to image the moon. All right, with that being said, catch you later.